In the previous lecture, I talked about how to compute a dot product for two vectors. So this lecture, I'm going to talk about the cross product two vectors. So cross product only refers to 3D vectors. It's a product for 3D vectors only. So for the dot product, as we know, dot product actually computes the product of two vectors. It returns a scalar value. Well, for the cross product, it actually returns also a vector value instead of a scalar value. Again, since we're talking about 3D vectors only here, if I have the C, which is A as a cross product of A cross B, now C is also a 3D vector, which means if I have sort of A vector is A1, A2, A3, so this is 3D vector, and then if B is B1, B2, B3. So C also has the same dimension, 3 dimensions, C1, C2, C3. Okay, so this is what it means. Okay, all right. So now we talk about how we actually compute this, and then we'll also talk about the physical meaning. Okay, so to compute the cross product of a 3D vectors, assuming here A vector is given by A1, A2, A3, and B vector is B1, B2, B3. Again, there must be three-dimensional vector. So my C vector is computed by doing this. So it's computed by it's obtained by computing the determinant of a 3 by 3 matrix. And so the key part becomes how do we put all those rows or columns, okay, for this 3 by 3 matrix to compute the determinant. So the first row will be the I and j's and k's vector, which talks about whatever. This will be just I. Okay, this will be j. This will be j, represent j, and this will be k. So this will be the first row, second row, and the last row. Okay. So the first row will be I and j and k. The second row will be the first one appeared over here. Okay, so here's A, so I put just A1, A2, A3 as a row. So put this one as a row. And because the second one in my cross product is B vector, so I put the B as the last row. So we try to compute all the cross product as a determinant. So it ends up, if it computes the cross product, the determinant we have this is A2B3 minus A3B2I plus A3B1 minus A1B3 times J and A1B2 minus A2B1K. Okay, so if you don't know how to compute the determinant, and go to my previous video talking about how to compute the determinant for a 3 by 3 matrix. Okay, so if you write this in the vector form, again, so this whatever value comes ahead of this I will be the value I call it C1. So this will be what we have for the C1. Okay, this value, just do it over here. Okay, and for whatever value comes before this J vector, this J is just this second one. Okay, and similarly, this will be for the K will be the last one. Okay, we put the value over here. So that gives us the C vector. Okay, so we also have the three-dimensional vector C. So this is how computer mathematically compute that. Similar to the dot product, we also can have some physical meaning for the cross product. Okay, so different from the dot product, which only gives us a scalar. So the cross product has both is a vector. So we have both the magnitude as well as the direction. Okay, so first of all, the magnitude of the C vector is magnitude of A cross B, because that's the same, right? That's the same. Okay, so which is the same as the magnitude of A times the magnitude of B times sine gamma. So this is different from the dot product. Dot product, this will be the cosine gamma. So the gamma again is angle between alpha A vector and B vector. Again, gamma should be less than or equal to 180, but greater than or equal to 0. So that's what it should be in. So even if B is going to the other direction, you don't have an angle which is greater than 180. Okay, this is what it means. So which means your magnitude cannot be negative, apparently, right? Okay, now let's speak of direction. So the direction is sort of direction. First of all, direction is orthogonal to this A vector and B vector, which means is orthogonal to the plane created by the A vector B vector. For example, if my A and B vectors are all in the X, O, Y space, for example, in this surface, and my C is perpendicular orthogonal to this surface, which means going pointing either up or pointing down. Okay, so how do we determine if it's pointing up or pointing down? It determines based on the right hand rule. So what this means, the direction of C is the sum direction when fingers move from A to B. Okay, if I'm going to draw my finger, okay, my finger is this. My finger, we'll draw my finger, okay, and this is my thumb, okay. So because this direction for my fingers, 4 fingers, this is pointing, okay, this is basically pointing. This is pointing to the perpendicular one. It's like this, okay. So because this direction, so you actually, your 4 fingers will mainly tell from A to B. Okay, so if I do this over here, so I'm actually moving from A to B. This, if I use my finger, you can tell it's kind of go up. Okay, if you let your 4 fingers move from A to B, your C will go up. Your thumb, the direction of the thumb will go up. If you swap the two, let's say B is starting from, let's say if it's B is here, well A is here, now your C will go down. Basically, this is your C direction because you go the other way around. Okay, you go A to B, right? So then you'll go down. Okay, and make sure the angle should be less than 180 degrees, so you don't go the other direction. You go, if this is A, this is B, you go basically this direction. So you're gonna go down. If you your fingers going according to this kind of counterclockwise direction, your finger will point down. So that's why the C will point down. Okay, so that's what it means physically. Again, so the magnitude is determined by the magnitude of the A times the magnitude of B times sine gamma. Gamma has to be in the range, angle in the range between 0 and 180 degrees. And the direction of C is determined by, first of all, is orthogonal to both A and B vector, which means it's perpendicular to the plane created by A vector and B vector. Second, the direction of C is the sum direction when things move from A to B. Again, I want to make sure gamma has to be less than 180 and less than 0. Okay. Okay, so here's what was this how you the physical meaning of the cross product. All right, now let's take a look at example how we compute this. Okay, so let's say if I give you A vector, which is 3, -2, 0, 4, 1, 5, so I can compute A cross B, which is I, J, K as the first row, and I put the second row as the A, whatever comes first. I put all the values right here as the second row, and then I put the B vector, the number in the B vector as the last row. Then I try to compute the determinant of 3x3 matrix. Alright, so without going into too much detail about how to compute the determinant, we actually have this. My I will be, here includes the steps, so detail how to compute this. You actually use the first row, okay? So try to compute the determinant for the 3x3 matrix. Basically, you have something times I, something times J, something times K. Okay, by computing the 2x2 determinant right over here, so I have I times -10, J times -15, and K times 11. So which is the same as a vector which is -10, -15, and 11. Okay. So one question is, what if I want to compute B cross A? What is this? Okay. So a simple way you can compute this, you can do, of course you can do this. I'm going to I, J, K. So I need to swap the order, right? So I have 4, 1, 5, 3, -2, 0. The reason I changed because I actually switched the order of the last 2 rows, because I switched order of A cross B to B cross A. Okay. So this one, if you compute it right away, you should have this. It's just negative sign. Change the sign. 10, 15, -11. The reason that's the case because I can actually infer this from the physical meaning. First of all, if you change the order, it doesn't change your magnitude. So it only changes direction. So if you change from A to B, it's still orthogonal to A to B, right? A and B, and the direction, you only change the direction. So if you change from A cross B cross C, you're going down. The direction, which means is negative of the. So which means my B important B cross A is just a negative A cross B. Okay, so that will make it much easier for you to compute the cross product for the other one. Okay. Alright, so let's talk about the property of the cross product. Okay, I already mentioned this product over here. So the first property is A cross B is negative of B cross A. As you mentioned here, why that's the case? You can infer this from the physical meaning. So the physical meaning says the magnitude does not change and the direction will change to the opposite direction. Okay. Okay, the second one property is C times A cross B and is equal to C times A cross B. So C is a scalar, which means if scale is this up and down of one vector, it doesn't change. It just scales in the same way, which is pretty straightforward from the physical meaning. If you say, first of all, if you scale it up and down, so you actually the magnitude will scale up and down, and the direction does not change, so everything will be the same. Okay, and also I have A plus B cross C is equal to A cross C plus B cross C. Okay, this one is a little bit hard to understand, but I think you can use this one to actually figure out why that's the case. Okay, which means if you do the A plus B cross C is the same as A cross C individually. Okay, you can write this individually. Okay, all right. Okay, so now let's talk about some of the special property for the since we're talking about three-dimensional vectors for the cross product. So there are a couple of the special three-dimensional vectors, okay, which is I and the J and the K. So I and the J for the three-dimensional one, I means 1, 0, 0, which is I's vector. J is 0, 1, 0. K means 0, 0, 1. Okay, so which means they are unit vector along x-axis, along y-axis, along z-axis. That's my I and what that means by I and J and K. So if you do the product, if you remember the dot product, I dot j is 0, j dot k is 0, k dot I, they're all 0 because they are perpendicular. In the dot product, the dot product all 0. Okay, of course the dot itself is 1. I dot I is 1, j dot j is 1, k dot k is 1. Okay, so for the cross product, a little bit interesting. So I cross j is k. Okay, j cross k is I. And k cross I is j. You do a circle. So I cross j is k, j cross k is I, k cross I is j. Okay, you basically do that. Of course, you can put a negative. So j cross I is negative according to the product over here. So it's negative that, negative that, negative that. And a cross itself is 0, 0, 0. It crosses 0 because the angle, you can use a physical meaning. Because the angle is gamma is 0. It cross itself is gamma is 0, so it's 0. Okay, so I cross I is 0, 0, 0, j cross j is 0, 0, 0, so k cross k is 0, 0, 0. Okay, they're all 0, 0, 0. Okay. All right. So next, I'm going to show you examples about the application of the cross product. Okay. So one example I give you here is how to compute the torque when let's say you use a wrench to actually move a boat. Okay, you want to compute how much torque you apply to the wrench. Okay, so in order to compute torque, you basically if I give you examples, this is my boat, so I want to use a wrench to actually move around. So assuming that okay, my hands right over here, I'm trying to apply a force somehow over here, trying to move the boat over here. Of course, there's a from the center of the boat to the point that I'm trying to apply the force, there's a vector over here. This is called R vector, and my force of course has a vector depending on which direction and how big. You could have smaller, larger, you can have change the direction, whatever you want to do. Okay, so the torque actually can be computed by R cross F. R is your vector from the center of the boat to the point you try to apply the force. And F apparently by its meaning is the force applied, including the magnitude and direction. Okay. So if I say my R is given by, if I talk about the XY domain, for instance, somehow like this. So this is XY, XY. So go up. This is Y. So of course this is coming up. Okay, coming out. This is coming out. So it's Z direction. So actually I can define this R vector. Let's say my R vector is 1.5, 1, 0, 0, and F is 100, 200, 0. That's the F, the force applied. So you can compute the torque as being M over here. So I can use definition over here. Try to compute the cross product. Okay, so the cross product is given by, first row is ijk, the second row is whatever comes first in my cross product, so it's a 1.500, and F last one is the force, which is 100, 200, 0. So you can compute that. So this is how we can compute this. If I do this one, I can actually have the, compute the determinant. So I can compute it, which is the final solution will be 0, I, 0j, and 300k. So that's where you can compute torque. So actually the torque means it's positive. You can see this one. So it means if I talk about direction, so the R, remember the R, the 50 minutes R going here, right? This is R direction, okay? F is over here, so it's from R to F. So from R to F. So it's from, if you remember here, the direction is from R to F. Okay, from R to F, and the angle should be less than 180 degrees. So this is R direction, okay, F. So it's coming actually inside, coming in. Okay, the direction coming in. This is torque. Okay, if you change the direction and force direction, it will change to the outside. Okay. All right. So that's all for the cross product.